Today let us solve Bessel's equation using Frobenius series method. Consider the differential equation x square y 2 dash plus xy dash plus x square minus n square into y equal to 0, where 2n is a non-integral value. Divide the given equation by x square to get a differential equation of the form y2 dash plus p of x into y dash plus q of x into y equal to 0. Then we have p of x is equal to 1 by x and q of x is equal to x square minus n square upon x square. Then p of x and q of x are not defined at x equal to 0. And x into p of x is equal to 1 and x square into q of x is equal to x square minus n square. Thus x p of x and x square q of x are analytic at x equal to 0. Hence, x equal to 0 is a regular singular point. Then the Frobenius series solution of equation 1, the given equation, will be of the form y equal to sigma m varying from 0 to infinity c m x raised to k plus m, where the coefficient c0 is not equal to 0. Here m is the variable of summation. Then we can find the derivatives y dash and y2 dash as follows. Substituting these values y dash, y2 dash in the given equation, we have a relation of this form. Here we can multiply x square and x raised to k plus m minus 2. Similarly, in this expression, we can multiply x into x raised to k plus m minus 1. And we can also multiply this factor into this sum as well to get the new equation as given here. Observe that the first, second and fourth series on the LHS has the general term x raised to k plus m. Now, grouping those series having x raised to k plus m as the general term, we get the relation as expressed here. If we group k plus m in the first and second term, we get the expression k plus m into k plus m minus 1 plus 1. That is k plus m whole square minus this n square into x raised to k plus m in the first series. We can also observe that the coefficient here contains a term, an expression of the form a square minus b square, which can be factorized as a minus b into a plus b. So that we get new relation as sigma cm into k plus m plus n into k plus m minus n into x raised to k plus m plus sigma cm x raised to k plus m plus 2 equal to 0. Now we can equate the coefficient of least degree of x in this expression, which is obtained when we put m equal to 0 in this series. That is, if we equate the coefficient of x raised to k in this expression to 0, we get a new equation which is known as the initial equation, which will be equal to c naught into k plus n into k minus n equal to 0. And since we have assumed that C0 is not equal to 0, we must have k plus n into k minus n equal to 0, which gives the roots k equal to n and k equal to minus n. So we can observe that the difference of these two roots will be plus or minus 2n, which is a non-integral value. So the roots of the initial equation are unequal and it does not differ by an integer. Now to obtain the recurrence relation, we equate to 0 the coefficient of x raised to k plus m. Then we obtain the coefficient in the first series would be Cm into k plus m plus n into k plus m minus n, and the coefficient in the second series on the RHS of the above equation will be Cm minus 2 equal to 0. Since the previous equation was like this, where the coefficient of x raised to k plus m plus 2 was Cm in the second series. So we need the coefficient of x raised to k plus m. Hence the coefficient would be obtained by replacing m by m minus 2. So that the coefficient would be Cm minus 2 in the second series. Thus we obtain the relation given here. Thus we get the recurrence relation connecting Cm and Cm minus 2. Now we can proceed to find C1 by equating the coefficient of x raised to k plus 1 to 0. We get C1 into k plus 1 plus n into k plus 1 minus n equal to 0, giving C1 equal to 0 for both k equal to n and k equal to minus n. Similarly, using recurrence relation, we will have C3 equal to 0, C5 equal to 0 and so on. Further, taking n equal to 2 in equation 6, we have C2 can be expressed as a function of C0. Now, putting n equal to 4 in equation 6 and using the above relation, connecting C2 to 0, we get C4 as an expression containing C0 and so on. Putting these values in equation 2, we get y equal to x raised to k into C0 plus C1x plus C2x square plus C3x square plus etc. will be obtained as a series of this form. Putting k equal to n and replacing C0 by an arbitrary constant a, we get this function which can be expressed as a into some u for convenience. Similarly, putting k equal to minus n and replacing C0 by another arbitrary constant, say b, we get a function y equal to bv. So that the required general solution can be expressed as y equal to au plus bv, where a and b are arbitrary constants.